Hi everyone, this is Charlene Joyce F. Malinao and I'm gonna teach you two topics under number theory. First up is relatively prime numbers. Perhaps you have met someone who you thought shared the same interests as you, but upon further discovery, you found out you didn't really have anything in common with this person. For example, maybe you met someone at the gym and this person said that he or she loves to go traveling, watch sports, and exercise. That sounds great since you like doing those same things as well. However, when you started talking to that person, you found out that his or her idea of traveling is camping and hiking out in the wilderness, and he or she enjoys playing and watching golf and tennis. You, on the other hand, prefer traveling overseas to large metropolitan cities and love playing and watching team sports like softball and soccer. Thus, it turns out that you actually have nothing in common with this person after all. A similar scenario happens in math with relatively prime numbers. So relatively prime is also called coprime. So relatively prime numbers have no factors in common other than 1. An alternate way to state this is that two relatively prime numbers have a greatest common factor or GCF of 1. Additionally, the least common multiple or LCM of two relatively prime numbers can be found by multiplying the numbers together because, by definition, the numbers have no factors in common. Please note that the numbers themselves do not need to be prime in order for the pair to be relatively prime. All that matters is how the factors of the numbers are related to each other. The notation of two numbers that are relatively prime numbers is this. So let's have an example. Let's take numbers 28 and 45. Are these numbers are relatively prime? So to determine if two numbers are relatively prime, you need to first factor each number into its prime factors. So the prime factors of number 28 is 1 times 2 squared times 7, while 45 is 1 times 3 squared times 5. Then you will compare these factors to see if any of them are found in both numbers. So we can see that the common factor of 28 and 45 is only 1. So obviously, they are relatively prime and their GCD is 1 and their LCM when we multiply the two numbers together is 980. So I have three facts for you about relatively prime numbers. So fact number 1, any consecutive positive integers are coprime. This is self-explanatory. So when we say consecutive, these are the numbers that are sequential, or these are the successive numbers. Let's take for example numbers 3 and 4, 906, 907, like that. And the next fact is if A, B are coprime, then A raised to M, B raised to N are also coprime for M and N positive integers. And the last fact, fact number 3, the probability that two integers M and N picked at random are relatively prime is 6 over pi squared. So let's move on to pairwise relatively prime. A list of integers is pairwise relatively prime if every pair of the items in the list are relatively prime. So please take note the words every pair. My second and last topic is about linear Diophantin equation. Let's have a history first. The word Diophantin is derived from the name of the ancient Greek mathematician Diophantus, who was one of the first people to consider such problems systematically. Diophantus was a Hellenistic Greek mathematician who lived in Alexandria during the 3rd century CE and wrote an influential series of books called the Arithmetica. It is one of the earliest known manuscripts on algebra. It is a collection of algebraic problems which greatly influenced the subsequent development of number theory. He is traditionally been known and sometimes called the father of algebra for manipulating and solving equations. Why he is known and called the father of algebra? Because he has a rival, and it is Muhammad al-Khwarizmi. So Muhammad al-Khwarizmi is a Persian mathematician who developed the concept of algorithm in mathematics and who is known in his great works Hisab al-Jabar wa al-Mukabala. So correct me if I'm mistaken in pronouncing his works. So these two mathematicians have greatly influenced and greatly contributed in mathematics, especially in algebra. So it's not official who is really among the two is the father of algebra. So who's your bet? Linear Diophantine equation is an equation where only integer solutions are accepted. So in a line, we can see that a line have infinitely solutions. But Diophantine equation is not interested with other real numbers or complex number solutions other than integers. So this implies that Diophantine equations becomes harder or even possible to solve. In algebra, it is required to find all solutions. Unlike the number theory, you're only interested with particular solution, which this additional restriction makes the problem more difficult. So let a, b, and c be integers and consider the equation ax plus by is equal to c. So we have 4 steps in solving linear Diophantine equation. First is to use Euclidean algorithm to find its GCD. So I hope that you're gonna watch our videos about Euclidean algorithm so you can know how to manipulate this algorithm, this topic. And the second step is to check if that equation is solvable. It is solvable if and only if the GCD of A and B divides C. The third is to use the reverse Euclidean algorithm. We're gonna solve for the remainders, then we're gonna substitute. And the last is to use the general equation to find the integer solutions. I have an example here of an equation that is not solvable. So the equation is 12x plus 21y is equal to 80. And to get the GCD of the numbers 21 and 12, we're gonna use the Euclidean algorithm. So let's the rule of the Euclidean algorithm is to take the larger number, which is 21, and we're gonna divide it to the smaller number, which is 12. So 21 divided by 12 is equal to 1 plus the remainder 9. That's what we get. So 21 is equal to 1 times 12 plus 9. So bring down 12 and that is 12 is equal to 1 times 9 plus 3, because when we divide 12 by 9, it will result to 1, and the remainder is 3. So bring down 9. 9 is equal to 3 times 3 plus 0. So the GCD of the numbers 12 and 21 is the number before 0, which is 3. And 3 doesn't divide 80, so it is not solvable. And 3 and 80 have a common factor of 1, and that is only 1. And 3 and 80 are relatively prime, so it's not solvable. We cannot go on with the next step, because 80 divide 3 is not an element of the integers. So let us note that not all linear Diophatine equations have solutions. I have here theorem 1.1. The equation ax plus by is equal to c has integer solutions if and only if ab divides c. If x sub o and y sub o is a solution, then all integers solutions are given by x is equal to x sub o plus b over ab times n, and y is equal to y sub o minus a over ab times n, where n is an element of integers, or the set of all integers. So I have here an example. Find the integer solutions of the equation 195x plus 42y is equal to 12. First step is to use the Euclidean algorithm to get the GCD. So I have discussed it earlier, how to get the Euclidean algorithm, and you can better learn about it if you're gonna watch our other video which focuses on this topic, Euclidean algorithm and the reverse Euclidean algorithm. So let's take the larger number 195 divided by the smaller number, which is 42, and that will result to 4 plus the remainder of 27. That is 195 is equal to 4 times 42 plus 27. So bring down 42, that is equal to 1 times 27 plus 15, and so on and so forth until you get the remainder 0. So the GCD of 195 and 42 is equal to 3. Step number 2 is to check if it is solvable. So 3 divides 12. So yes, it is solvable. And we're gonna proceed to the next step, and that is use the reverse Euclidean algorithm, then substitute. So the left part is what we had solved earlier, the Euclidean algorithm. So we're gonna use this to solve the reverse Euclidean algorithm. So we're gonna solve 4 remainders. So 27 on the uppermost equation that we have, which is 195 is equal to 4 times 42 plus 27, and the remainder is 27. So see the uppermost part of the right side, which is the remainder is 27, is equal to 195 minus 4 times 42. The same way the other remainders, which is 15 is equal to 42 minus 1 times 27, and then the remainder 12 is equal to 27 minus 1 times 15, and last is 3 is equal to 15 minus 1 times 12. So that are our remainders, 7, 15, 12, and 3. And we're gonna substitute this and we're gonna use the remainder 3, which is 3 is equal to 15 minus 1 times 12. So we have number 12 here, the 12 here, and we're gonna substitute. 12 is equal to 27 minus 1 times 15. So 3 is equal to 15 minus 1 times the quantity of 27, but that is the value of our 12, which is 27 minus 1 times 15. So distribute and take note that the what inside the parenthesis is a variable. Take note ha. The inside of the parenthesis is a variable. So 12 is a variable, and the number beside it is a number, or is a constant. So when we distribute 1, so we're gonna have 3 is equal to 15 minus 1 times 27, then plus, because negative times negative is positive, plus 1 times 15. Then combine like terms. So 3 is equal to 2 times 15, because 15 plus 1 times 15 is equal to 2. And 15 is a variable, so at is lang siya. So 2 times 15 minus 1 times 27. Then substitute 15, which is 42 minus 1 times 27. See the upper part of our reverse Euclidean algorithm. So 3 is equal to 2 times the quantity of 42 minus 1 times 27. Bring down 1 times 27. Simplify. 3 is equal to 2 times 42 minus 2 times negative 1 times 27 is equal to negative 2 times 27. Then bring down 1 times 27. Then combine like terms. We have the same variable, which is 27. So negative 2 times 27 minus 1 times 27 is equal to negative 3 times 27. So in the right part, substitute 27, which is 195 minus 4 times 42, and that will be 3 is equal to 2 times 42 minus 3 times the quantity of 195 minus 4 times 42. So simplify again. 3 is equal to 2 times 42 minus 3 times 195 plus negative 3 times negative 4 is 12, and the variable 42. And then the 3, we're gonna make it 12, because our c in the ax plus by is equal to c, and the original equation is equal to 12. So we're gonna multiply it by 4 to make it 12. So 4 times 3 is equal to 12. 4 times 14 is equal to 56. And then the variable 42 minus 4 times 3 is equal to 12. And then the variable 195. And then we're gonna use the general equation to get our solutions. So we're gonna make our equation to the original equation, which is ax plus by is equal to c, and that turns out to be 195 times negative 12 plus 42 times 56 is equal to 12. So our initial solution, which is x and y, our x is negative 12 and our y is equal to 56, and we're gonna use this initial solution to get our general equation and our some integer solutions. So we're gonna use the formula x is equal to x sub o plus b over AB times n, and then substitute. That will result to x is equal to negative 12 plus 14n. The same way with y, gonna substitute it, and y is equal to 56 minus 65n. So that is our general equation. So we're gonna let n be any integers. So I have here let n is equal to negative 3. Let's just substitute it. So x is equal to negative 12 plus 14 times n, which is negative 3. Simplify. That will result to x is equal to negative 54. The same way with y. Substitute n, which is negative 3, and y will be 251. So our second solution is negative 54, 251. And we can use any integers of to substitute the n. I hope you understand. So corollary 1.1, suppose that AB is equal to 1, or the GCD is of A and B is 1. Then the linear equation ax plus by is equal to c has integer solutions for all integers c. If x sub o, y sub o is a solution, then all solutions are given by x is equal to x sub o plus bn, and y is equal to y sub o minus an, where n is the set of all, or is an element of integers. So I have here an example. Find the integer solutions of the equation 141x plus 34y is equal to 30. So we know our first step is to use the Euclidean algorithm to find the GCD. I hope you know it. What is a Euclidean algorithm about? So let's take the larger number, which is 141, divide it by the smaller number, which is 34, and that will result to our quotient 4 plus the remainder 5. The same way, the same process until we get the remainder 0. So the number before 0 is 1. So that is the GCD of 141 and 34. Step number 2 is to check if it is solvable. GCD of 141 and 34 is equal to 1, and 1 divides 30. So it is solvable, and we can proceed with the next step. Next step is to use the reverse Euclidean algorithm, then substitute. So on the left side is our Euclidean algorithm. We can use this to solve for the remainders. So 5 is equal to 141 minus 4 times 34. Then 4 is equal to 34 minus 6 times 5. And 1 is equal to 5 minus 1 times 4. And then we're gonna substitute these remainders. So we're gonna start to 1 is equal to 5 minus 1 times 4. Substitute 4, which is 34 minus 6 times 5, and take note that the what is inside the parentheses is our variable. Okay, it is a variable, it is at ease. So our 1 is equal to 5 minus 1 times 34. We're gonna simplify it, plus 6 times 5. So combine like terms. 5 plus 6 times 5 is equal to 7 times 5. Bring down negative 1 times 34. So we're gonna substitute 5. 1 is equal to 7 times the quantity of 141 minus 4 times 34. Bring down negative 1 times 34. So simplify. 7 times 141 minus 7 times negative 4 is 28. And then the variable 34. Then bring down negative 1 times 34. So our original equation, the value of C is 30. So we're gonna make 1. We're gonna multiply 1 to the number that will result to 30, and that is 30. So 1 times 30 is equal to 30. 30 times 7 is equal to 210 times 141. Then 30 times negative 29, it result to 870, negative 870 70 times 34. So step 4 is to use the general equation to find the integer solutions. Gonna transform our equation to the original, to the ax plus by is equal to c equation, and that is 141 times 210 plus 34 times negative 870 is equal to 30. So our initial solution is 210, and that is x, and negative 870, which is our y. So using the formula, which is x is equal to x sub o plus b n, and y is equal to y sub o minus a n, and it will result to x is equal to 210. We're gonna substitute it plus 34n. 34 is our b, which is and y is equal to negative 870, that is the value of our y sub o, plus 141, that is a, then n. So let n is equal to be any integers. So I let my n is equal to 1 to make it easy to solve. So substitute x is equal to 210 plus 34 times 1, and that is x is equal to 254, while y is equal to negative 870 plus 141 times n. Simplify, y would be equal to negative 729. So our second solution, or our other solution, is 254 and negative 729. So we can use other integers in n. So I hope you understand, and you can comment down below your questions or your additional informations. And now I challenge you to answer this one. So Clara wants to buy pizza and cola to her family. She has $400. If we know that each pizza is $57 and each bottle of cola costs $22, how many pizzas and bottles of cola she can buy? So I encourage you to answer this, and I have a quiz for you if you want to answer my two topics, the relatively prime numbers and the linear Diophatine numbers. So thank you for watching and listening to my discussion, and please hit like and subscribe to our channel.